Hello students, so welcome back to my video lecture 4 on P block elements. So from the previous video we are talking about the chemical properties of boron family elements. We discussed three important chemical properties. What is it? Okay, one, reaction with oxygen, correct? Then reaction with what? Nitrogen, then reaction with water. Did we complete? Reaction with water. Did we complete these three reactions? Yes. I told you that boron family elements react with oxygen to form two types of oxides. Which are those two types of oxide? One is E2O3, the other one is E2O. Which are those elements which form oxides of this type? Yeah, it is boric oxide, aluminium oxide, gallium oxide, S, and indium oxide, isn't it? Only thallium will form oxide of the type E2O, isn't it? Next, what about the reaction with nitrogen? I have told you that gallium, indium, thallium, they do not react with nitrogen, isn't it? They do not react with nitrogen. Only boron, only aluminium reacts with nitrogen of the air to form nitrides of the type Bn and Aln. What happens when these nitrides are hydrolyzed? They liberate ammonia gas, correct? And I've told you if boron nitride molecules come together, they form inorganic graphite. How about the reaction with water? How does boron family elements react with water? Yes. So we know, boron or gallium or indium or thallium, they do not react with water, isn't it? They do not react with water. Only aluminium reacts with hot water to form what? Aluminium oxide, and it liberates hydrogen gas. So all these three reactions are complete in the previous video itself. Now we shall go with the other chemical properties of boron family elements. The other chemical properties of boron family elements. What is it? Next, reaction with acids and bases. Next reaction, the fourth reaction. Reactions with acids and bases. Acids and bases, isn't it? Reactions with acids and bases. Just a minute. So reaction of boron family elements with acids and bases. See, we know we have boron, aluminium, gallium, indium, and thallium, isn't it? See, we know boron is a non-metal, correct? Boron is a non-metal, whereas aluminium, gallium, indium, thallium are metals. Well, aluminium is what type of metal? It's an amphoteric metal. Aluminium is an amphoteric metal. Amphoteric metal means this reacts both with acids and bases, isn't it? Reacts both with acids and bases. Any doubts? Aluminium, being an amphoteric metal, reacts both with acids and bases, whereas these are simple metals, they react only with what? Acids. Reacts only with acids. Yes, only with acids. Then how about boron? Will it react with acid or will it react with base? Let us understand that later. But before that, let us see how aluminium react with acids and how aluminium react with bases, and also how gallium, indium, and thallium reacts with acids. So let us understand these reactions first before we talk about what? Boron. Understood? Now look here, very simple reaction. Don't worry about balancing the reactions. Okay, don't worry about balancing the reactions. So I can say aluminium reacts both with acids and bases because it's an amphoteric metal, whereas gallium, indium and thallium reacts only with acids. Okay, now see this, see the reaction. So what happens when aluminium reacts with HCl? What happens when aluminium reacts with sodium hydroxide? Sodium hydroxide. So this is an acid and this is base. Okay, yes. What happens when aluminium reacts with acid and what happens when aluminium reacts with base? Of course, look here. Okay, how do we write the reaction? Just you have to interchange what? Interchange the ions. I told you. Okay, correct. Aluminium exists in its oxidation state 3 plus. In HCl we have H plus Cl minus, isn't it? Now, okay, so this cation will react with this anion, isn't it? Okay, correct? Okay, this cation will react with this anion. So what is the product formed? Any idea? Okay, what is the product formed? Yeah, it will form what? Aluminium chloride. Okay, Al3 plus Cl minus. Okay, interchange, crisscross method. Aluminium chloride and it liberates which gas? Hydrogen gas. It liberates which gas? Hydrogen gas is liberated. Hydrogen gas is liberated. Okay, so aluminium reacts with acid to form aluminium chloride and it liberates hydrogen gas. By the way, what happens when aluminium reacts with a base? It forms a peculiar compound. I have told you this in S block elements. Didn't I? I have told you this in S block elements. Okay, aluminium reacts with the base to form what? NaAlO2 and it liberates hydrogen gas. What is this NaAlO2? This is called as sodium aluminate. Sodium aluminate. Got it? Okay. What is this called as? Sodium aluminate. Okay, no doubts, understood? Okay, so when aluminium reacts with acid, it forms aluminium chloride and it liberates hydrogen gas. When aluminium reacts with the base, it forms a very peculiar compound. What is that peculiar compound called as? Sodium aluminate. There also it will liberate which gas? Hydrogen gas. Okay, yes, that's correct. Now what about gallium, indium and thallium? Okay, these three will react only with acid. Then how do they react with HCl? Okay, gallium, indium and thallium. Yes, okay. So how does gallium reacts with HCl? How does indium reacts with HCl? And how does thallium reacts with HCl? So gallium reacts with HCl to form what? Gallium chloride of the type what? GaCl3 and it liberates hydrogen gas, isn't it? It liberates which gas? Hydrogen gas. Indium reacts with hydrogen chloride to form indium chloride, InCl3. This liberates hydrogen gas. Correct? Okay. Yes. Thallium reacts with hydrogen chloride to form thallium chloride of the type TlCl because thallium exhibits only what oxidation state? +1 oxidation state. Remember that point. And it liberates which gas? Hydrogen gas. Understood? Okay, so like that. So gallium, indium and thallium react only with acids, whereas aluminium reacts both with acids as well as a base because it's an amphoteric metal. Understood my point? Okay, that's great. Then how about boron? Will boron react with acid or base? Now let us treat boron with sulfuric acid. Okay, look here, boron okay, does not react with dilute acids. Okay, it reacts only with concentrated acids. Only with what acids? Concentrated acids. Okay, boron does not react with dilute acids. It reacts only with what type of acids? Concentrated acids. Are we clear? Okay, now what happens when boron is treated with concentrated sulfuric acid and what happens when boron is treated with concentrated nitric acid? Look here, in this case See, these acids does not act as acids. These acids, okay, in this case, in reaction with boron, okay, acids act as oxidizing agents. Act as what? Oxidizing agents. They do not behave as acids, but they behave as what? Oxidizing agent. That means in this case, concentrated sulfuric acid will act as oxidizing agent. It will oxidize boron to boric acid, boric oxide, B2O3, or okay, it will oxidize to BOH thrice, and it liberates sulfur dioxide gas. Okay, and nitric acid will also act as oxidizing agent. It will oxidize boron to boric acid, and it liberates which gas? Nitrogen dioxide gas. So like that, when boron reacts with concentrated acids, because it does not react with what? Dilute acids. Boron does not react with dilute acid. It reacts only with what acids? Concentrated acids. So when boron is reacting with concentrated acids will act as what? Oxidizing agents. Okay, so these acids will oxidize boron to, okay, boric acid. Okay, sulfuric acid will oxidize boron to boric acid. It liberates sulfur dioxide gas. Okay, nitric acid will oxidize boron to boric oxide, and it will liberate which gas? Nitrogen dioxide gas. Nitrogen dioxide gas. Okay, any doubts? No doubts? Okay, are we clear? Yes, wonderful. Okay, now we have a question on this concept. What is that concept? Can nitric acid or can sulfuric acid be stored in aluminium vessel? Yes, look here. Okay, can nitric acid or sulfuric acid be stored in aluminium vessels? Aluminium vessels. Okay, what is the answer? Can nitric acid or sulfuric acid be stored in aluminium vessel? The answer is yes. Okay, concentrated nitric acid and concentrated sulfuric acid can be stored in aluminium vessel. Why? Look here. Yes, when okay, nitric acid or sulfuric acid is stored in aluminium vessel, okay, the inner layer of aluminium, okay, aluminium will react with nitric acid, to form what? Okay, yes, what does it form? Aluminium hydroxide, and it liberates nitrogen dioxide. Okay, this aluminium hydroxide will further decompose to give what? Aluminium oxide. It will further decompose to give aluminium oxide. Are you getting my point? Aluminium, the inner layer of aluminium, see this inner layer, the inner layer of aluminium which is in contact with nitric acid, okay, will react with nitric acid to form aluminium hydroxide. Aluminium hydroxide will further decompose to give what? Aluminium oxide. That means there is a formation of a thin layer of aluminium oxide here. There is a formation of thin layer of aluminium oxide. See, this we have already learned. When there is a formation of thin layer of aluminium oxide, this layer of aluminium oxide will prevent further oxidation of aluminium. That means aluminium becomes passive. Correct? Aluminium becomes what? Passive. Say yes or no? Okay. So the inner layer of aluminium will react with nitric acid to form aluminium hydroxide, which will further decompose to give what? Aluminium oxide. So that means there is a formation of thin layer of aluminium oxide inside. This thin layer of aluminium oxide will prevent further oxidation of aluminium. That means aluminium becomes passive. Therefore, I can store nitric acid or sulfuric acid in aluminium vessel, because nothing happens to nitric acid or nothing happens to the concentration of sulfuric acid, okay, once there is a formation of thin layer of aluminium oxide, okay, once there is a formation of thin layer of aluminium oxide, okay, further oxidation of aluminium will be prevented. Therefore, okay, there will be no further change in the concentration of nitric acid, or there will be no further change in the concentration of sulfuric acid once aluminium becomes passive. Once aluminium becomes what? Passive. Therefore, can we store nitric acid and can we store sulfuric acid in aluminium vessel? Yes, we can store it. Why? Because nothing happens to nitric acid and nothing happens to sulfuric acid once there is a protective layer of aluminium oxide formed inside the aluminium vessel. Okay? Is that simple? Aluminium becomes passive. Aluminium becomes what? Passive. Okay? Understood? Yes, that's so nice. So that's about the reaction with acids and bases. Now, next reaction. Reaction of boron family elements with halogens. Okay, look here. Reaction of boron family elements with halogens. Fifth reaction. Reaction with halogens. Okay, that is what? Fluorine, chlorine, F2, okay, F2, Cl2, Br2 and I2. Fluorine, chlorine, bromine and iodine. Okay, reaction of boron family elements with fluorine, chlorine, bromine and iodine. Look, okay, again let us take boron, aluminium, gallium, indium and thallium. Okay, what about the stable oxidation state of all these elements? Boron will be in +3 oxidation state, aluminium in +3, gallium in +3, indium in +3, whereas thallium will be in +1 oxidation state, isn't it? Okay, so therefore what happens when these boron family elements reacts with halogens? Look here, when boron reacts with halogen, it forms halide of the type BX3. Okay, why BX3? Look here, boron +3 oxidation state, halogen -1 oxidation state. Now apply crisscross method. Don't you think it is BX3, isn't it? Okay, so when boron reacts with halogens, they form halides. What is the formula for halides? It is BX3. Okay, on the same lines, aluminium reacts with halogens to form aluminium halide. What is the formula? AlX3, because again aluminium is in which oxidation state? +3 oxidation state. Gallium reacts with halogens to form halide of the type GaX3. Indium will react with halogens to form indium halide of the type INX3, whereas thallium reacts with halogens to form thallium halide of the type TLX, isn't it? Why TLX? Because thallium will be in +1 oxidation state, halogen will be in -1 oxidation state. Correct. Now cross multiply, what is that you're going to get? TLX, isn't it? Yes. So from boron to indium, these elements reacts with halogens to form halides of the type EX3, isn't it? From boron to indium, okay, so these elements reacts with halogens to form halides of the type what? EX3, whereas thallium reacts with halogen to form halide of the type what? EX. Are we clear? So that means I can say, okay, now boron family elements reacts with halogens to form two types of halides. One is EX3 and the other one is EX. Okay, boron to indium, okay, they form halides of the type EX3, whereas thallium is going to form an halide of the type what? EX. Any doubts with this? Any doubts? So if I consider the halides of boron and aluminium, look here. Yes. Okay. Well, understand this point here. So I have halides of boron. Let us understand the halides of boron. Okay, so among halides of boron I have boron trifluoride, because we know, okay, boron will form halides of the type what? BX3, isn't it? Boron will form halides of the type what? BX3. So we have boron trifluoride, boron trichloride, Okay, boron Tri Bromide and boron triiodide. Okay, we have boron trifluoride, boron trichloride, boron Tri Bromide and boron triiodide. Okay, note this point, boron trifluoride and boron trichloride, these two are gases. Okay, boron trifluoride and boron trichloride are gases, whereas boron Tri Bromide and boron triiodide, this boron Tri Bromide is a liquid, whereas boron triiodide is a solid. This is a solid. Understood? Okay, so boron trifluoride and boron trichloride are gases, boron Tri Bromide is a liquid, boron triiodide is a solid. Can you tell me why boron triiodide is a solid? Okay, yeah, why boron triiodide is a solid? Can you tell me? Okay, see, we have fluorine, chlorine, bromine and iodine, isn't it? Okay, so as we go down the group from fluorine to chlorine, as we go down the group, the size will increase, correct? Atomic size will increase. As the atomic size increases, van der Waals force increases, isn't it? As the atomic size increases, van der Waals force increases. This we have studied in states of matter, isn't it? Okay, as the size increases, as the atomic size increases, van der Waals force increases. Van der Waals force increases, correct? Okay, so as the force of attraction increases, all the molecules will come closer and closer, closer and closer. When all the molecules are close to each other, when all the molecules are close to each other, what do you call this state of matter? This is nothing but solid state, isn't it? This is nothing but what? Solid state. Is that correct? So here also, as we go from fluorine to iodine, boron is common here. Boron is common, no doubt in it. But as we go from fluorine to chlorine, size increases. As the size increases, van der Waals force increases. As the van der Waals force increases, all the molecules, all boron triiodide molecules will come closer and closer, closer and closer. When they come closer and closer, when all the molecules are close to each other, what do you call that state of matter as? That is nothing but what? Solid. Understood? So that is why boron trifluoride and boron trichloride are gases, whereas boron Tri Bromide and boron triiodide, boron Tri Bromide is a liquid and boron triiodide is a solid. Okay, it is a solid. Understood? Now again consider, look here, yes, boron trifluoride. Okay, boron trifluoride, BF3, correct? BF3. Boron trichloride, BCl3. Okay, boron Tri Bromide, BBr3, BBr3, correct? And boron triiodide, Bi3, isn't it? Boron triiodide, it is Bi3. Okay, so boron trifluoride, boron trichloride, boron Tri Bromide and boron triiodide. Okay, in all these cases, boron is sp2 hybridized, sp2 hybridized. Since it is sp2 hybridized, what is the structure? Trigonal planar structure, isn't it? Trigonal planar structure. Okay, it is here also boron is sp2 hybridized, therefore the geometry is trigonal planar. Here it is sp2 hybridized, therefore it is trigonal planar. Here it is sp2 hybridized, therefore it is trigonal planar. Here also it is sp2 hybridized, that is why it is trigonal planar. Correct? Any doubts? Now look at the central atom here. Here boron is surrounded by how many pairs of electrons? Well, boron is surrounded by 1, 2, 3, 4. One bond means 2 electrons, isn't it? One bond means 2 electrons. So boron is surrounded by 1, 2, 3, 4, 5, 6. Is that correct? So boron is surrounded by 6 electrons. Boron, the central atom is surrounded by 6 electrons, isn't it? It is deficient of 2 more electrons. It is deficient of 2 more electrons to complete its octet. to complete its what? Octet. Am I correct? So boron, the central atom, is surrounded only by 6 electrons. It is still deficient of how many electrons? 2 more electrons to complete its octet. Okay, here also boron trichloride, in boron trichloride also, look here. Okay, so this central atom is surrounded by 1, 2, 3, 4, 5, 6. Okay, here also the central atom is surrounded by only 6 electrons. It is deficient of 2 electrons, correct? So like that, if you take any trihalide of boron, if you take any trihalide of boron, all the trihalides of, in all the trihalides of boron, boron is electron deficient. Okay, boron will be electron deficient. Electron deficient. Are you getting my point? Okay, so okay, in all the trihalides of boron, boron is electron deficient. Electron deficient. Since boron is electron deficient, okay, it is ready to accept the electrons. Since it is ready to accept the electrons, it acts as what? Electron acceptor. What do you call the electron acceptors as? Okay, it is deficient of 2 electrons. Okay, boron in all the trihalides, it is deficient of 2 electrons. Since it is deficient of 2 electrons, it is ready to accept 2 electrons. What do you call, okay, a pair of electron acceptors as? Yes, they are called as what? Lewis acids, isn't it? They are called as Lewis acids. Lewis acids. Say yes or no? So that means I can just quote, okay, all the trihalides of boron, all the trihalides of boron are electron deficient and hence okay, acts as Lewis acids. Is that correct? Hence they act as what? Lewis acids. Lewis acids. Okay, so boron trifluoride is a Lewis acid, boron trichloride is a Lewis acid, boron tri bromide is a Lewis acid, and also boron triiodide is also a Lewis acid. Okay, then which among them is a strong Lewis acid? Okay, what is the order of acidity among these trihalides of boron? Which is a best Lewis acid? Which is a strong Lewis acid? Which is a strong Lewis acid? Is it boron trifluoride or boron trichloride or boron triiodide or boron tri bromide? Which one is a strong Lewis acid? Okay, look at the order of acidity here. Yes. Well, okay, so if I consider, okay, order of acidity, if I consider the order of acidity, okay, yes. Consider the order of acidity, look here, boron triiodide seems to be a strong Lewis acid, then boron tri bromide, then boron trichloride, okay, boron trichloride, and then boron trifluoride. Okay, boron triiodide is a strong okay, Lewis acid, okay, Lewis acid, then boron tribromide, then boron trichloride, and then boron trifluoride. Okay, remember this order of acidity. Why is this order? Why boron triiodide is a strong Lewis acid? Why boron trifluoride is a weak Lewis acid? Why is that? Okay, let us consider the structure again. See this. See, if I consider boron trifluoride, okay, so when boron is forming bond with fluorine, okay, look here, so here, okay, 2p orbital of boron will overlap with 2p orbital of fluorine, and there will be one vacant orbital in boron. There will be one vacant orbital in boron. Okay, whereas when it forms boron trichloride, okay, look here, when it forms boron trichloride, okay, again here also there will be one vacant orbital in boron, okay, and here 2p orbital of boron will overlap with 3p orbital of chlorine. Got it? Okay, now when you go with boron tribromide, understand this, here also there will be one vacant orbital, but okay, 2p orbital of boron will overlap with 4p orbital of bromine. And lastly, with boron triiodide, okay, yes, in triiodide, there will be one vacant orbital, no doubt in it, but 2p orbital of boron will overlap with what? 5p orbital of iodine. Okay, since, see, there is 2p orbital of boron and 2p orbital of fluorine. Okay, look here, we know halogens will have 3 lone pair of electrons. Okay, see, okay, fluorine will transfer, okay, 1 lone pair of electrons from its 2p orbital to 2p vacant orbital of fluorine, and it forms a vacant, and it forms a back bond. So because of back bond, okay, boron, the electron deficiency of boron is fulfilled, isn't it? So guys, let us talk about okay, the order of this acidity in the next class. Okay, thank you.